Hello, today we're going to talk about section 5.3, the fundamental theorem of calculus. Now, we motivated the fundamental theorem of calculus when we talked about our worksheet from section 5.2. In particular, on the second page, we talked about a function, capital F of x, which was the area accumulation function for how much area was accumulated under a curve little f of x. So in this example, what we saw is that we defined capital F of x as the area from 0 to x of f of t dt. Now, when we were talking about area from 0 to 5, we saw that this is just going to be our standard area under this curve, and we were able to compute several values quite easily. We had to be a little bit careful when we went backwards because we started at 0. If I was looking at, for example, f of -1, I would be looking at the area in this blue rectangle. But of course, when I look at that area in the blue rectangle, I'm going to switch the signs. So I'm going to look at the area from 0 to -1 is the same as the area from -1 to 0. And so in the end, I get a -1. So that was our capital F of -1. Now, what else do we have to notice? We noticed a lot of features about this. Now, even though we were very careful and we saw that this function was increasing on the interval from -infinity, assuming it keeps going off to the left, to +5, and then it was decreasing after -5. Now, the reason it starts to decrease there was we started to add negative area. Remember, when we talk about integrals, we're talking about we're talking about signed area. So when we start to be below the x-axis, our area starts to decrease in this case. So this should remind you a lot about some of the basic properties of derivatives. So for instance, we know with the derivative of a function, when a function is increasing, its derivative is above the x-axis. And when a function is decreasing, its derivative is below the x-axis. And we see the same features happening in this graph, right? Above the x-axis is where little f is, and we see capital F, the area is increasing. Same thing with below the x-axis on the interval from 5 to infinity. We could also think about when that area is increasing, and we could talk about when the area is increasing faster. When you start to think about the rate at which something is increasing, you could talk about the second derivative, or concavity. So here are the answers here. You can pause it here if you want to check your own answers, but I'm going to move on and summarize what we've just discussed on a separate slide. So my first bit of summary is that where f is positive, a sub f, or f, is increasing. Where f is negative, little f, the area accumulation function is decreasing. One other thing we saw, which I didn't talk about, is that where little f is 0, the area accumulation function has a stationary point. We also saw that if little f is increasing, capital A sub f is concave up. And we saw little f is decreasing, means that we are adding area at a slower rate, so a little capital A sub f is concave down. So in this case, our key takeaway is that the area accumulation function being defined from a to x of f of t dt for any behave function. In this case, we want our function little f to be continuous, and we want it to actually contain the point, continuously defined on an open interval that contains our starting point, little a. Then a sub f is an antiderivative of little f. So, in other words, if I take the derivative of a sub f of x, I should get back to the function f of x. So let's do an example. So let's say that f of x is equal to 2x sine of x squared. And then I can let the area accumulation function of f of x be equal to the integral from 0 to x of f of t dt. Well, one thing I'd like to do is I would like to find a formula for a sub f of x. Well, I know that a sub f of x is an antiderivative of little f. And if I look up at little f, this looks like a familiar function. So I see that I have an x squared inside my parentheses, and then I see outside of my parentheses I have the derivative of x squared, 2x. So my guess for the antiderivative is that my a sub f of x should be negative cosine of x squared plus c. Well, first thing I would like to do is I need to figure out what is plus c, because I need to actually find a single formula for the function that works. So one thing I know is I know that a sub f of 0, well, 0 to 0 accumulates no area, so that should be 0. So now if I plug in that into my cosine function, that should be equal to negative cosine of 0 squared plus c, or in other words, that should equal negative 1 plus c should equal 0, which tells me that c has to equal 1. So now I know my exact formula using this initial piece of information. I know that a sub f of x is equal to negative cosine of x squared plus c. In the next example, we're going to make it a little bit simpler. We're not going to find the actual formula, but let's say that I want to find the derivative of the area accumulation function of the integral from 0 to x of sine of the tangent of t dt. So when I see something that looks like this, I think that my little function f is really sine of the tangent, and I want this to be f of x, oh, don't need a dx. Sine of tangent of x. And we know that in this case, the a sub f of x is equal to the integral from 0 to x of sine of tangent of t dt, or in other words, it's equal to the area from 0 to x of f of t dt. And so what my fundamental theorem of calculus tells me is that the derivative of a sub f of x is just equal to sine of tangent of x. So your problem for the warm-up is to find the derivative of the area accumulation function from 0 to x of 1 over 1 plus t to the 5th dt. To prove the second part of the fundamental theorem of calculus, we want to use the following fact, which is that if two functions have the same derivative, then their antiderivatives differ from each other by only a constant. We can use this fact to prove what's called the fundamental theorem of calculus part 2, which is Theorem 4 in your book. So Theorem 4 says that if f is continuous on the interval from a to b, and f is any antiderivative of little f, then the definite integral from a to b of f of x dx is equal to this antiderivative evaluated at b minus the antiderivative evaluated at a. So let's see how we could prove this. So we know that if f is any antiderivative, so f is an antiderivative, we also know by the first part that capital A sub f is an antiderivative of little f. So what this can tell us is that tells us that f of x is equal to a sub little f of x plus c for some c by our fact. So if I want to compute the quantity f of b minus f of a, I can say this is a sub f of b plus c minus a sub f of a plus c. And when we do this, we see the little c's cancel out, and we get a sub f of b minus a sub f of x. And the way we defined a sub f of here, we can define it as the integral from a to b of f minus the integral from a to a of f. And this thing is just 0 because it's the integral from at just a point. And so this gives us our definite integral from a to b of f dx. So this is an extremely useful theorem. What it says is that if I want to compute the area under the curve, I just have to find an antiderivative and take the difference of the antiderivative evaluated at the endpoints. So, for instance, let's let f of x equal x cubed. So if I want to compute the area from 0 to 1 of x cubed dx, what I can do is first I can find an antiderivative. We know an antiderivative for x cubed by the reverse power rule is x to the 4th over 4. So this is equal to f of 1 minus f of 0, where these are the capital F's. So in other words, this is going to be 1 to the 4th over 4 minus 0 to the 4th over 4. And when I simplify this, I just get 1/4. Now let me just show you how we normally write this in calculus class. We're normally going to write this as the integral from 0 to 1 of x cubed dx. And normally I don't do the extra step of finding the antiderivative separately. I just say I'm going to evaluate the function, the antiderivative x to the 4th over 4. I could choose a different value of c, but I usually just choose c equal to 0 because it doesn't matter. I can choose any antiderivative, and I put these endpoints 0 and 1 here, which just does the same thing I did up here. So it's going to be 1 to the 4th over 4 minus 0 to the 4th over 4. which gives me 1/4 again. So I usually use these square brackets here to simplify my work a little bit. So your second problem, and the last one for today, is to evaluate the definite integral from 1 to 4 of the function 6x minus 2 dx. So that's all for today. We'll practice a lot more with definite integrals in class on Wednesday. Have a good night.